All right, so just playing around, I made a program called go.c, which defines x to be a floating point number and sets x equal to 2 times 10 to the 33rd. And then it multiplies x by 10 and prints out the value of x, multiplies x by 10, prints the value of x, and so on. Yeah?
What does the .c mean? Like go.c? Does it reference something? Or?
It's like p1.c. So the .c is the convention we use for a C program.
Okay.
Technically, I think you could make it anything you want. But if you say GCC, it's looking for a .c. So I'm going to set x to 2 times 10 to the 33rd and keep multiplying it by 10 and printing out its value. And if I do that, you can see it works for a while and then it gets too big, and now when I print out x, it actually says INF, which means infinity. Right, so it's a valid floating point number that is used to represent something too big to actually convert to a floating. Now, it's not actually infinity, right? But effectively, right, so what's infinity? Infinity is not a number, right, mathematically. Infinity just means something bigger than any number that exists. So it's not a number itself, it's something that's larger than any number, and that's kind of what this means here, right? It's larger than any possible valid floating point number. This is what one teacher I used to know called junk code, right? Junk code is awesome. It's not that it's code that's worthless. It's code that you're writing just to do something, and then you're just going to sort of like get rid of it and move on, right? This doesn't do anything that I'm going to need in the rest of my life. It's just a way to experiment with some stuff. I wanted to see what happens if I take this number and keep multiplying it by 10 and it gets too big. If this is an integer, let me make a different version of this. Let me try this with integers. Right, if it's an integer, when my integer gets too big by multiplying by 10, it turns into some weird number. Right, I multiplied, I think that's 1 billion times 10, and I got 1.4 billion. And I multiply that by 10, I got 1.2 billion, and I multiplied that by 10, and I got negative something, right? That's just crazy. But when you do this with floating point numbers, it does something more reasonable. Right, so that's another advantage of real numbers, floats and doubles. They have this reasonable handling of overflow and underflow. So x equals x star 10. Evaluate the right-hand side, and star means multiplication. So take the current value of x, multiply by 10, and then the equal sign, remember, is an assignment. It says take that thing and copy it over to the value of x. So it's changing x to be 10 times its original value. And this is a lot of what we do in programs as we modify the values of variables, read them, make some change, combine them, and then store that somewhere. So we call these things expressions, okay, or arithmetic expressions. And it's basically a combination of operators, things like add, subtract, multiply, divide, and operands, which are numbers or variables, things that represent values. And the value of the expression is what you get when you apply those operations to those operands, right? It's just like plain old algebra, 2 plus 3 times 5. And plus, minus, add, subtract, stars, multiply, slashes, divide, we understand those pretty well. Percent is a weird operator. It's what we call the modulus operator. Percent is a way to divide two numbers and figure out what the remainder is. So for example, if we take 12% 2, that says take the number 12, divide by 2. Well, that's equal to 6. How much is left over? 0. This is equal to the value 0. If we take 12% 5, It says take 12 and divide by 5. Well, 5 goes into 12 2 times. That gets you to 10. How much is left over? 2. So that's got a remainder of 2. 12% 7. Well, 7 goes into 12 once. That gets you to 7. How much do you have left over? You have 5 left over. So this is the remainder. If we do A % B, it's the remainder of A divided by B. And that's useful for various things. Now, a lot of times we'll do something like x equals x plus y, or A equals A plus B. We do this enough that C actually gives us a shortcut way of representing this, which is we can just say x plus equals y, or A plus equals B. And this means exactly the same thing as that. X plus equals y means take the current value of x, add y to it, and then set that equal to x, or assign that to x. It's a shorthand. Even more common is this, x equals x plus 1. We do this all the time. I equals I plus 1, j equals j plus 1. And we could write this as x plus equals 1. But there's actually another shorthand we can use for this, which is just x plus plus. I'll throw my semicolons after here. But this could be in the middle of some other. So x plus plus means exactly the same thing as x equals x plus 1. Any idea why we have these shortcuts?
To make the coding more efficient.
To make the coding more efficient. It's actually, it's a little easier for us to write x plus plus than x equals x plus 1. But earlier compilers, it's a whole lot easier to understand x plus plus versus x equals x plus 1. And since incrementing a variable x equals x plus 1 is so common, it's really nice to be able to recognize when that's what's happening. And so the earlier compilers would see x plus plus, they would actually turn that into a different kind of instruction, an instruction that ran a lot quicker on the CPU. Today, probably doesn't make any difference, right? A good compiler, if I say x equals x plus 1, it's going to do the same thing as if I say x plus plus. But back decades ago, right, early compilers, it was letting the human do some of the work for the compiler by saying, like, hey, this is actually an increment instruction. So plus equals is like x equals x plus something. Minus equals, times equals, slash equals, percent equals, same thing, right? So, so g star equals x is the same thing as g equals g times x, and so on. All right, just like with regular algebra, there's an order of operation. And there's an acronym, PEMDAS, that you can use to remember what gets higher priority. So parentheses get the highest priority. Things in parentheses get evaluated first. Exponentiation, raising something to a power, comes next. Multiplication, division come next, and then addition, subtraction are the lowest priority. So if you do something like 1 plus 2 times 3 plus 4. What do we got? We've got addition, multiplication, and addition. The rule of precedence says multiplication gets done first. So multiply 2 by 3, that's 6. Now our expression is 1 plus 6 plus 4, that's 11. If we really wanted to add 1 and 2, and then add 3 and 4, and then multiply by those two together, use parentheses. Right? Parentheses have higher precedence than multiplication, so this will happen first, and this will happen, and those will get multiplied, and you'll get 21. If you're in doubt, use parentheses, right? You can be explicit in what you want to have happen when by using parentheses. But after a while, you get pretty comfortable with this sort of default order. Multiplication, division, or higher precedence, basically. The heck's going on here? Most of these things we haven't talked about yet. But basically, most expressions we can evaluate from left to right. Okay, the way that we would normally do it on paper. But there are things called unary expressions, right? Expressions that only take a single operand. The classic example is the minus sign. -7, that says -7, okay? We're not subtracting 7 from something, we're actually just saying this is the number -7. So if I say 5 times -7, that's going to give me -35, right? It's not like the multiplication somehow gets higher precedence. This is actually treated as a single entity. And up here on the second row, you can see the plus plus expression, minus minus expression, right? Those things take precedence also. So if I do 5 times x plus plus, right? That x plus plus should happen first. Increment x and then multiply that by 5. There's some nuances to using this plus plus minus minus business that I think we'll get into another time. But you'll see sometimes x plus plus and sometimes you'll see plus plus x. And they're slightly different from each other. But that would take us far afield.
So why is C++, the language is called that?
Yeah, so C++ is a language, right? And the plus plus is a bit of a nod, I think, to the fact that we can increment things in C by saying plus plus. So C++ is supposed to be like the next version of C, I think. So it was incremented. But it's a totally different language. It's like C, but it has objects in it. So it's an object-oriented version of C. Now, I don't know if this is true or urban myth, but a student told me this. So have you heard of C#? So C# is Microsoft's version of Java, basically, right? And what my student told me he had heard was that this is like C+++++. So it's supposed to be the better version of C++. I don't know if that's true or not. It's a good story. All right, so b equals minus a. The minus sign is negating a to be -10, and then setting b equal to -10. So casting is something that we can do in most languages. For example, here we've got a, which is a float. It's a real number. We've got b, which is an integer. A is 34.7. We want to take that value and store it in b. Well, b is an integer, right? 34.7 is not an integer number. So let's try this without a cast. Set a equal to 34.7, say b equals a, and then let's print out the value of b. I was hoping it was going to give me an error. It's okay. So it sets b equal to 34. I really wanted it to give me an error. So technically I'm taking a float and I'm trying to store it in an integer, and floats don't store in integers, right? Different types of boxes. But it'll do the best it can, right? It will convert it to an integer in some hopefully reasonable way. But if we want to explicitly say convert this to an integer, we can do what's called casting it. So in parentheses we put in a type of variable, in this case int, and we say, okay, turn this into an int. And it will try to do that in some reasonable way. Let's talk about comments. So here's my p1.c. The C language is really small, right? We said there were like 20 or 30 keywords to it, and it's a combination of those keywords. And this program's pretty straightforward. Once you understand how C works, it's pretty straightforward to know what's going on in here, right? A, B, C are integers, we're initializing B, we're setting C to a value, and so on and so forth. But imagine a program that's 10,000 lines of this kind of stuff, right? That's been written by a team of 15 people over a period of 6 months, 10 years ago. And now you're trying to work with this code, right? And you didn't write it. It may not be so clear when you come in and you start looking at this code and you're responsible for this set of 500 lines, right? It may not be so clear what's going on because all the stuff starts to look the same. So we can add other things into the source code that have no effect on how the program runs. They're strictly there to let people who are looking at the code understand better what's going on. Okay, so these things are called comments. And one thing we can do with comments is we can put information, say, in the beginning of the program to tell the reader what this program is. What the heck am I looking at? What's p1.c, right? But we can also put comments on lines of code or sections of code to help explain what's going on in these different sections. So there's a couple of ways we can put comments in a C program. One way is if we have 2 slashes, everything else on the line after those 2 slashes is ignored. Okay, so I could say // B is the number of students in the class. And let's put back our A equals 10. And let's put a comment here saying A is the number of new students coming into the class, and B is the current number of students in the class. And so this is the new enrollment for the class. Okay, it's a little silly because C equals A plus B is pretty self-explanatory, but you know, imagine this was buried in like tons of code. Now, you know, yeah, C equals A plus B, but you know, I know that C is the enrollment in the class after we've added these new students, right? And so we go on and we do some other stuff. And you know, so let's show the user how we got to the new enrollment. So we're going to put some print statements in there. And comments are completely ignored by the compiler. Right? So nothing will happen based on your comments, usually. There's a few exceptions. Okay, so we can say // everything else after that is ignored. The other thing we can do is we can say /*, and then we can start typing a bunch of stuff on multiple lines. And all of this is part of a comment. And when we want to end the comment, we can just say */ and that marks the end of it. So a single line comment on a line of code, you can just say // but sometimes you don't want to keep saying // So you just say /* and you start putting in all of your information. So we might make a block of comments like all right, and so that's all like just a block of comments. Has no effect on the compiler. And commenting is another one of these topics. If you go online, you'll find all kinds of political wars over the subject of how much should we comment, should we comment. I write such good code that it is self-documenting. It doesn't need any comments, right? That's a common line you hear from people. And yeah, if you use good coding style, your code can be largely self-documenting. But depending on what the code is doing and how large it is and how many pieces are in it and what language you're working in, right, some degree of commenting is almost always a good idea. If you work in assembly language like in Engineering 270, you probably comment every single line of code. Because the statements are so small, they're doing such a tiny little thing. We can't even add two numbers together in one statement. It takes 3 statements to do something like C = A + B. Right? So sometimes we do a lot of commenting. And it's another aspect of programming style, right? And you know, some people will do things like you know, put all their comments over a certain number of spots so that they all line up no matter how long the lines are. Right, some people like that, or they'll indent them one by one so the slashes look like diagonal lines. There's all kinds of stuff you can do, but it's just something to be aware of. But no effect on the code. Okay, so back to the modulus operator. Remainder when you do A divided by B. So 20 mod 10 is 0, 15 mod 10 is 5, 38 mod 15. 15 goes in twice, that gets you to 30. You've got 8 left over, so you get an 8. And why do we use a modulus operator? Well, there's different places where this pops up. So there's a clock, except it's only got one hand and it's got a 0 instead of a 12. But it's basically a clock, right? And right now it's 2 o'clock. And suppose we're going to wait 15 hours. What time is it going to be on our clock if we go 15 hours forward? It's going to be 12 hours will bring us back to 2, 13, 14, 15. It's going to be 5 o'clock. Well, if we take 2 plus 15 and we calculate that modulo 12, this is 17 modulo 12, that's 5. That's not a coincidence. Clocks basically calculate time modulo 12. So if we go forward 100 hours, what time will it be? 102 modulo 12. And there's things like this that pop up all over the place in programming, pops up inside operating systems, where you want to go down to a certain point and then wrap back over to the beginning. And so that's one place where modulos come into play. Testing to see if one number divides another. So how many people here know anything about prime numbers? Oh, we're going to have fun in CSE 215. So prime numbers are numbers that are divisible by only themselves or 1. Okay, so yeah, so So 2 is prime because it's only divisible by 1 and 2, itself and 1. 3 is divisible by 1, it's divisible by 3, it's not divisible by anything else, so that's prime. 4 is divisible by 2, so that's not prime. 5 is divisible by 1, not by 2, 3, or 4, it's divisible by 5. Every number is divisible by 1 in itself, basically. But does this number have any other factors? Well, 6 is divisible by 3, so that's not prime. But 7 is prime. 8's divisible by 2, that's not prime. 9 is divisible by 3, that's not prime. 10 is divisible by 2, that's not prime, but 11 is prime. So you can start making a list of these numbers that are not divisible by anything other than the things they have to be divisible by themselves in 1. These are called prime numbers. Prime numbers rock. They are central to the universe in ways that we don't understand yet, but they permeate everything. And if you find me on Steam, I'm Prime Minister 37. It's been my handle since I was a kid, without the 37. But prime numbers are just like, they're fascinating. And they're really simple to explain. We just explained them in a minute, right? And there are thousands of years worth of work on some very basic problems related to prime numbers that have never been solved. For example, is a number prime, right? Here's a number, 1001. Is that a prime number? There's no fixed, easy way to tell other than just trying to divide by all the possible numbers that might divide it. This turns out to be 7 times 11 times 13, so it's not prime. But there's no algorithm for telling if a number is prime or not. If you take any even number, like 16, you can write that as a sum of 2 primes. I can write 18, well, I can't write 9 plus 9 because 9 is not prime, but I could do 5 plus 13, right? Or I could do 7 plus 11. There's a postulate that any even number bigger than 2 can be written as a sum of 2 primes. Never been proven, never been disproven. It's called Goldbach's conjecture. And people have made inroads into this, and people have discovered new areas of mathematics trying to study this, but nobody's proven it, nobody's disproven it. And there's just tons of problems like this around prime numbers. So if you want to figure out if a number is prime on a computer, what can we do? See if something divides it. How do we tell that? Use the modulo operator. Right? So take your number %2, take your number %3, your number %4, and so on. If your number % something is 0, it means it divides evenly. There's no remainder. So you write a program that basically keeps dividing your test number by successive integers, and if it finds one that divides it, it's not prime. If you go through all the possibilities and none of them divided it, it is prime. That's a project you'll do later on in this course, by the way. Condensing a large range of numbers to a smaller range, so that's kind of like the clock thing, right? We want to know what time it is. We don't want to say it's 105 o'clock, right? Even though technically it might be. We want to reduce it to something from 0 to 11, so we can use a percent modulo operator. So here's a snippet of code. It's got some more includes in the top because we're using functions like this thing called random and this function called time. And just like printf, we have to say include stdio.h. If you're going to use time, you have to include time.h, and so on. So there's more includes. There's the integer main void curly bracket that we always have. I is an integer generated as an unsigned integer, and then we're doing this thing called srandom, unsigned time null. Don't worry about what that means. The purpose of that is to basically initialize the random number generator, a random number generator, to be starting based on the current time, so that every time you run this program, it'll do something different. And then this is a for loop. We have to talk about those, but basically these statements here between these curly brackets, here and here, these statements will get executed 10 times. And each time it's going to call this function called random, which is going to give us a random unsigned integer. That's a number from 0 to 4 billion. Well, a random number from 0 to 4 billion isn't much fun. When you say think of a number, you don't want them to think of a number between 0 and 4 billion. You usually mean like a number between 0 and 10, right? So instead of taking a number from 0 to 4 billion, if we take that number and we say, oh, he doesn't say it in here. Oh, I got time to type this in. I can't select it though. So generated is a number from 0 to 10 million. If we were to say something like this, generated equals generated percent 10, we're saying take this number that could be up to 4 billion, divide by 10, tell me what the remainder is. Well, the remainder is either 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. So it's a way to generate a random number between 0 and 9, basically. And that might be more useful for what you're trying to do here. So that's a number from 0 to 9. What if we wanted a random number from 1 to 10? Just add 1 to this thing, right? So take this, add 1, now we've got a number from 1 to 10. And now we can play a guessing game if we want. All right, so let's, I don't really want all those comments in there. Okay, so we're back to our original. Okay, so let's look at this program again. Let's look at this printf statement. Okay, so this printf statement, when we run this, it prints out 10 plus sign 20 equals sign 30, right? And that's somehow related to these variables a, b, and c that I've listed over here, because a is 10, b is 20, c is 30. But there's this business here in the middle, this percent I plus percent I equals percent I, that's kind of weird, right? Here's the basic story with printf. I can say printf, put in a double quotation mark and put in anything I want, and everything from there up to the next double quotation mark gets printed. So if I say print that was easy, it prints out that was easy. But if I say that was easy backslash n, it doesn't print out a backslash followed by an n, it prints out a new line, right? Because back n is a way to say print out a new line. Okay, so that just goes down to a next line. So sometimes the stuff you put inside quotation marks doesn't actually come out verbatim. Sometimes it's interpreted in some way. And that's what's happening in this first printf statement where we have these percent i's. Percent I says, hey, after this quotation mark ends, I'm going to have some commas with variable names in them. The first variable that I list, find its value and print that out in place of this percent I. The next time there's a percent I, it says, hey, actually there's going to be 2 variables listed after this. Take the second variable, find its value, print it out. And this one says, take the third value, find its value, print it out. And so it's basically, this is a placeholder for what will eventually be the value of A. This is a placeholder for the value of B. This is a placeholder for the value of C.
Is I for integer?
I is for integer, exactly.
You don't have to define I.
No, so this is part of the printf instruction, and there's a reference that I might have handed out. If not, it's on Canvas anyway, that shows you what you can use inside this printf. Yeah?
When do you use percent D versus percent I?
I always use percent %d. I don't know if there's any difference. There probably is, but it may be one of these differences that effectively never comes up. So if I'm typing quickly, you'll probably see me use percent %d, but Scott seems to be using percent %i, so I would stick to percent %i. And so this is down here, right? If you have an integer, do percent %i or percent %d. And it's got to be an int. So suppose I make C a double, right? I can take 10 and 20 and add that together, I get 30. That can be stored as a double, right? That's a valid double. But if I print it with a %i, I get 10 plus 20 equals 0, which isn't quite right. Right? Why? Because this %i is expecting an integer and I'm giving it a double. It has no way of knowing that's what happened. Sometimes the compiler will tell you, hey, there's a problem. So if I want to print a double, I should use a %e, %f, or %g. I usually use %f. So if I change this to a %f, right, 10 plus 20 equals, and it showed me my value 30, but it printed it out with a .000 because it's a floating point number. So it looks like it's a floating point number. And sometimes you write your code and it's not working and you spend all this energy trying to figure out what's wrong with your code, and the only thing that's wrong with it is the way that you're presenting the print statement. And you're trying to print it out as an integer when in fact it's a double, and that's why it's always saying it's 0 or it's some crazy number.
How would you like make it only read the first two decimal values?
So we can get into, I don't know if he does that
Why
in here.
does it print out 8? Yeah. It's the same question.
So he doesn't do that in here, but if I say %3f, that didn't work. Okay, so if I say .3f, that means put in 3 digits after the decimal point. If I say 10.3f, that says use a total of 10 places before the decimal point and 3 after. A total of 10 with 3 after. And so there's all these different ways that you can control the format. If I do negative 10.3f, that makes it left justified. So printf is one of these things that here's a one-page synopsis of how to use it, right? Print a character with %c, integer with %i or d, floats or doubles with %f. Those are the main ones for now. But we can also print out in hexadecimal, base 16, using a %x. And again, if you go to manual section 3, chapter 3 in the manuals, and you look for printf, somewhere in here you may find some of this information. Now this page describes printf, fprintf, sprintf, snprintf, vprintf, vfprintf, etc., etc. A whole bunch of different versions of printf, but the documentation for them is effectively the same. So it describes some of the particulars, but the formatting of these things. So the format string, right, and you can read all of this, but who wants to do that? So the character % is followed by 0 or more of the following flags. So number signs, zeros, dashes, spaces, plus signs, and so on and so forth. And so this will describe everything about how to use the printf statement, but it's way too much to read, and really the better way to do it is just to mess around with it. Right? Maybe do a bit of Googling to get some examples, but don't get too heavy on Google with this stuff. Google will really sort of shortchange you on the learning part. Right? It'll give you an answer, but discovering is so much more powerful than having someone hand something to you. Right? When you discover something, it gets coded in your brain in a fundamentally deeper way. So let's do something like this. So let's just make some floating variables, give them some values, and print them out with a printf statement. And I'm just going to start with just plain old %f. So with no embellishment on the %f, it just sort of prints them out in what it considers to be a reasonable way. And they're sitting side by side, and it looks like 6 digits after the decimal point. So if I say %10f, right, it prints them out, but they're forced to take up 10 spaces. Let's make it 20. Okay, so now it's really clear what's going on, right? They're right justified, and if there's not enough stuff to fill in 20 spaces, it just puts spaces in on the left. If I make it -20f, that left justifies, which is probably what we wanted. Right, so now it's x equals, and our number starts right after the equals sign, but the stuff is lined up now, right? If I were to print out multiple things on multiple rows, they would all start in those same spots, because I'm filling out the stuff to the right until I've taken up 20 spaces. And again, if we do like 20.2, without messing it up. Right, now they're left justified 2 digits after the decimal point. Total of 20 columns for each. And printf is really powerful, right? You can get very sophisticated with the formatting. You can start putting other things in the beginning and so on and so forth. I'm going without a safety net here. Let me see what happens if I do this. Right, so if you put 0 in front of the number of decimal places you want, it'll display your numbers, but it will pad any extra space with zeros. Right, so that's still pi, but it's just not the way we normally write it. It's got a bunch of zeros in the front. So lots of options and possibilities there. All right, questions on that so far?
It's not going to do any rounding for you.
It kind of will. That's a good question.
Change that to 2. Right. It's probably just truncation, right?
Let's just do 3.555 for x. So that rounds to 3.56. So 0.5 or higher goes up. Yeah.
So looking ahead to next week's homework, there's like a table that we need to make. You
Mhm.
can use this to make like a pseudo table, but is there a better way to make a table that we're going to go over?
You mean to display the output?
Yeah.
Yeah, so this is exactly what you're going to end up using.
Okay.
is different versions of printf. So program 2, which you can start looking at and thinking about, well, we'll go into this full bore on Tuesday, You're running a convenience store and you have 3 items: oranges, energy drinks, and yogurt, right? And each of these has a certain price. Oranges are per pound, and drinks and yogurt are just per item. Oranges are non-taxable. Everything else has a tax rate of 6.5%. And your goal is to write a program which asks the user how many pounds of oranges they have, how many energy drinks they have, how many yogurts they have, and then prints out a nice little table like this. So item, cost, tax. Oranges, if you got 1.75 pounds of oranges, and they're 95 cents a pound, it should calculate the cost of the oranges is 1.66, and there's no tax. You got 3 energy drinks at 150 each. Total energy drink cost is $4.50. It should calculate the tax as 0.29. And then you've got 4 yogurts, 75 cents each. That's $3, and it's taxable, so 0.19. And you should round this to 2 decimal places. 2 decimal places. And then add up the total for the cost, total for the tax, combine those, print out a grand total. All right. So we're going to start working on the algorithm for this, and we're also going to talk about how to do input, which is to use something called scanf. It's kind of the flip side of printf. But we'll start talking about how we would take this task and break it down into a series of steps, and then how we can take each of those steps and write C code that will perform those steps one at a time. And it's going to be a matter of asking the user how many pounds, getting that number from the user, asking energy drinks, saving that number somewhere else. So we're going to have some variables for storing these inputs from the user, and then doing some calculations to find the cost and the tax, and then some clever use of printf to print out a nice table like this. Do some arithmetic and multiplication to find the total cost, add in the tax, and get our grand total. So we'll do this as a class. We'll go through at least doing this for oranges, and then we'll talk about how we extend it to also include the other items as well. And we'll definitely talk about scanf, because that's the input side, and that takes some explanation on how to do that. And this will be P2, and you've got some time to do this, but we'll start working through this as a class on Tuesday. All right, that's all I got today. Have a good rest of the week, good weekend. I will see you on Tuesday.